Okay, folks. Eagle Mine. Eagle Mine is really a late-breaking thing that sort of got put on us all, but it's a very interesting site with a lot of interesting things, with a lot of problems. I'm going to skip across. This project is not really a project. It's a regulator. The Yukon government is a regulator, and there's ECC and ECCC and DFO, and there are many lots of Indigenous groups watching this closely. And really, the GSC is a pretty small player in this. There's just a few of us, and we're just helping out where we can. That's really the bottom line. So when it's not really a project that we're running, it's a big mine site emergency response that we're reacting to, and that's really between myself, Alex Debray, and Alexandra, and this emergency response is really done by task forces. There's task forces on all sorts of things. The three we're really involved with is the off-site task force. That's Plume environmental chemistry. On-site and on-site is hydrogeology. And then the contamination task force, which Alex is sort of participating in to some extent in geomicrobiology because of the cyanide content. But there are many other task forces that we are not involved with, and like the actual heap leach failure and the biology, the fish habitat and those kind of things. There's task forces on those too. So we play a small but important role in helping the task forces. So what is Eagle? This is the Eagle mine site on June 26, 2024, suffered a major failure of the heap leach facility. Which slid down the gully there, which is called Dublin Gulch. It was the estimate is about 2 million cubic meters of the heap leach facility failed. And the estimates vary between 200,000 and 800,000 cubic meters of cyanide-rich heap leach fluids got released during that time. And as you can see with Haggett Creek there, they just go down the gulch and into the creek. There was clearly this is a major environmental problem, a major failure. Very fortunately, there was nobody injured. The failure happened when nobody was, it was mid-afternoon, if I recall, what people have told me, and there was just nobody in its path. But as you can see, it had a kilometre of run out and a very large failure scar there. It kept moving for quite a while. It stopped moving sometime over winter, but there's still questions as to whether it will start moving again in the summer, that failure. So there's real problems in this mine site, and the emergency response has basically been to try and figure out how to deal with this problem. Okay, so this is sort of the lower, if we go back to just looking for beyond there down the lower part of Dublin Gulch there from is where this next slide is. And so you can see that the circled area there is the toe of that slide. For a large part of the time, because everything was moving, that was a no-go zone. It was too hazardous and we couldn't get in there. But the first thing was, how do we actually track what's going on? How do we monitor the environmental footprint of these fluids and so forth getting out? Because there wasn't many data points to be had. So over time, we basically, group of us basically worked on trying to figure out what were the sources and how fast were things moving. The hydrogeologists were trying to numerically model it. Even to this day, that really hasn't worked for many complicating factors. And as you can see, we set up basically 4 lines of interception and monitoring wells and data collection points, which now total close to 8,000 analyses since June 26, 2024. A huge database that we will learn a lot from in due course. The first one is right at the toe of the slide. There's a line there. Then you see the lower Dublin settling pond there. Then the next line of monitoring is through LDSP there. And then the next line is sort of right through MW10. And then the next line of monitoring is through the creek itself at W22 and W4 mix. There is so much data. I'll only really talk to you about LDSP, MW10, W22, and W4 mix just to keep it somewhat simple. But there is a lot of data and a lot of analysis required because of that. First thing was, well, okay, where do we set up the monitoring? Where do we set up the interception? By interception, I mean where a production well where we can pump contaminated water back out of the well and into containment so that it's not actually impacting the environment. So there's monitoring and interception network for both surface and groundwater. Well, we started analyzing all the data and we sort of came to some conclusions about how to model it, and sort of we essentially figured out that there were at least three through breakthrough curves and aquifer end member modeling. We basically came that there were at least three water sources within the gulch. And as you can see, the black arrow there, that was one that was not expected. It was a little gully, but it actually contributes quite a lot of groundwater. And the breakthrough curves, as they successively go down through the gully, suggest that the plume is moving on average about 10 meters per day, which is fast. So that took a lot of time, that modeling. It took a lot of, because sometimes you got to wait for it to get there before you can model it. But yeah, that was important. So if we look at the plume history, this is a couple of plots. One is LDSP, that, as I talked to you about, which is Upper Dublin Gulch, representative of Upper Dublin Gulch chemistry, and then W4 mix, which is Haggart Creek. And as you can see, they for these plotted parameters, cobalt, copper, and sodium sulfate, cyanide, initial surface runoff increased in the Upper Dublin Gulch. Some of those ions by 1,000 times. It's a huge amount of contaminant increase into those areas. Took a little while longer for it to register in Haggart Creek, but due to dilution from the creek, it only increased by about 10 times for some of those contaminants. And then in Haggart Creek, it decreased after about a month. That surface runoff declined, and that input declined. But that wasn't, of course, the end of the story. The groundwater started coming in, and of course, the plume soon enough reached the creek. And as you can see in the W4 mix there, specific conductivity, cyanide, cobalt, all increase over time to 100 times. So these are values above aquatic health guidelines by some margin. So this is not a good outcome. And they've remained high ever since the fall increase as the plume impact impeded on the creek. It's actually increased. It's actually stayed level. The freshet is now just about upon us, and that's going to decrease them, and that's a good thing. But intercepting that plume and stopping that plume is really still the name of the game that we haven't really been able to do yet. I'm going to talk also at the end, because it's a way of introducing the modeling that we did, about discharges and unexpected impacts. And those little bumps in the copper and cobalt and so forth curves towards the end of the line, towards the end of the record in W4 mix there. Curveballs. Any emergency response will tell you that there's always curveballs. Mercury was one that was fairly early on. And it was because there's no mercury in the leach solution. So when you look at LDSP there, mercury suddenly jumps by 3 orders of magnitude or 2 orders of magnitude at very short order. And not in the same, in a longer time frame, but even in a W22 in the creek itself, it increased as well. Well, it didn't take much to work out. There was legacy placer mining in this area from 1900 through to at least 1960, and some people think it was even going through to 1980 where mercury was used. And it's pretty clear that this mercury is legacy placer contamination. But it's an unknown amount. We have no idea how much was used or how much is sitting in the soils. So that's a significant problem. And in the spring, there's a good chance we're going to be starting to do soil sampling, which will actually give us a better handle on what might be lurking in there. Unfortunately, mercury readily complexes with cyanide and mobilizes, which is why you suddenly get that rapid peak, because it basically says, hello, I'm off, time to go and party. But the decline was, over the fall, we thought, oh, okay, well, this is a depletion of that legacy mercury pool. We were sort of like, okay, this is good. Yeah, it's bad, but it improves with time. As soil moisture returns in the spring, unfortunately, mercury is starting to show its face again. So perhaps we haven't got rid of the pool and we still have a problem there. Time will tell, but that is not a story we thought we were through, is not there yet. Discharges. So I talked about interception a little bit. Well, interception is a two-edged sword because you've got to store that water somewhere, and this is a mountainous terrain. You can't actually have ponds everywhere, and you can't indefinitely amass contaminated water. You've got to get rid of it somehow, and the plan is, of course, to treat that water so it's below guidelines, and but it's actually good water again, and then release it. But that's proven difficult. There's been a lot of engineers been working on the water treatment plant, and realistically, it's only in the last couple of months that we've started getting treated water and being able to discharge it. But then we discharged it, and we found some really weird effects. So on that graph there, you'll see the straight lines there. Those are the levels of concentrations in the discharge pool. So if you look at cyanide and copper there, the actual cyanide and copper in the creek are higher than the discharge. They go up higher than the discharge. How could that possibly be happening when the creek is adding to dilution? It should dilute. Clearly hasn't. Cobalt, on the other hand, has done the opposite. It's way below where you hardly see a blip there. It's got high levels coming in and then suddenly disappears. Also, the concentrations seem to peak and then decay. That's an indicator that we're talking about sorption here. And I think that the data from even the accidental spill early on, but on the discharges, suggests this is a sorption story. So I took off and did some modeling, and there's the discharge in the Haggart Creek water for the PE, pH, specific conductivity is different, but they're not too dissimilar. What it turns out is there's actually a really subtle interplay between mobilizing ligands in this thing. As I told you, cyanide is pretty good at mobilizing mercury, but it's also good at mobilizing copper and iron too, whereas it's not that good at mobilizing cobalt. And iron is really an interesting story that will come back up more in the next slide. But what it shows is clearly that there is at least a little bit of iron mobilization, a lot of copper mobilization, and a lot of cyanide mobilization by decreasing cobalt. So what you've had is an exchange chemistry where cobalt is basically, you've had sorbed cyanide and copper in the substrate that is being released and replaced by cobalt. And so the cobalt, cyanide, and copper are being released into the water. So essentially, you've got an exchange chemistry going on. That is what we think now is a pretty short-term effect. So hopefully it's not an ongoing problem, but we haven't had a long enough discharge period to be really 100% sure of that. It's also limited. The modeling has a limitation here, and that is there's not a lot of thermodynamic data on different cyanide species because there's a lot of different cyanide species. And so that limits to where the amount of modeling you can actually do here. But you can also do groundwater modeling. And I'm going to talk about here between LDSP and MW10. So that's Upper Dublin Gulch and Mid Dublin Gulch, still both in the Dublin Gulch. Now, if you actually look at cyanide and copper there, cyanide decreases by over an order of magnitude between those two sites, and copper by 4 orders of magnitude. It's a huge decrease. There's actually even though the specific conductivity doesn't change that much, there is quite a large change in ion chemistry. There's also a high variability in MW10 thermodynamic data. What you see is that it's really a story about iron and redox processes in between those two. What you see in MW10 is evidence that there's actually reduced iron, even to sulfide in some summer samples, sulfate reduction to sulfide. So you've got both oxides and sulfides. It's a very complicated story, suggesting there's active Fe2 plus Fe3 plus exchange in the subsurface. That's sort of bad news because if you look at the second line there, Prussian blue, you don't want to form this ion Fe2 plus CN6. That's a very stable ion. with reduced iron, and then forms all sorts of precipitates, Prussian blue being just one of the well-known one. There's Prussian white, there's all sorts of different iron cyanide precipitates. So you've actually got the redox conditions change between LDSP and MW10 to suggest there's actually potential to precipitate iron cyanides. And that's going to take a lot of ions with it, copper being one of them. And so we don't have a lot of data between LDSP and MW10, but in the spring, there's now plans to do some drilling in there to see if we can actually understand exactly what's going on between those two. That redox change is concerning and points to a data gap, even within this very large data set. Again, that modeling it's taken quite a lot to do, but it's actually important because it's provided an idea as to why we got such a radical decrease between those two sites. Okay, I'm going to leave it there because there is an awful lot I could talk about. Numerical hydraulic modeling has not really been worked in this area. That's partly a permafrost story. That's partly a lack of hydraulic conductivity data. So Brendan Mulligan, a hydrologist, I'm going to frame this on one email, said, all we know about the plume comes from its chemistry. And that's really what it still is. We know how it's acting, how it's behaving, what it's doing through its chemistry and the modeling of that chemistry. I haven't talked about the microbial work, which is really still ongoing. Permafrost, there's a permafrost story here. It's a very complex one. The permafrost surface is really complex. I don't think anybody really understands it, but it's undoubtedly shaping the subsurface and surface flows. Sequential leaches are ongoing, all important data, but we're sort of still playing those out. As I said, modeling indicates the plume is moving about 10 meters per day, at least 3 end-member water sources. Mercury is a legacy in contamination that's been remobilized by the plume, which is really unfortunate, but it's a reality we have to deal with. The ion chemistry has identified the underlying chemical processes and zones with insufficient information. That's really important to understand. And I think in the long run, there's this large database, and this unfortunate incident is going to be a big help in learning what things we can and cannot do in permafrost terrains and in these kind of mines. And thank you for listening.